but for now we're going to pass it on to George, who's going to lead us on Objective 3. Over to you, George.
Yes, first of all, great to be back and listen to all the great research scholarship that is being produced with Objectives 1 and 2, and soon from the rest of the objectives. Here today I am presenting for the next 30 minutes or so the progress that has been made on the Objective 3 with the title Develop Estimates of Hydrological Process Controls on Carbon Sequestration and Greenhouse Gas Fluxes from Wetlands in Agricultural Landscapes. So just to give you a bit of context that this objective, in essence, we're trying to develop models of wetland carbon cycling, connect them with the erosion and the runoff processes, and basically understand that the interplay that drives the exchanges among wetlands and between wetlands and other water bodies. There is a wonderful team associated with this particular objective: Ali, Pascal, Irina, Dave, and Christian, and also an impressive number of technicians, postdocs, and graduate students that a small sample of the students involved, I will have the opportunity to highlight their work during the presentation. The objectives, the tasks involved for this particular objective, this is the official party line, what we submitted in the proposal, and involves the use of data collected across our network of wetland sites to develop process-based models of carbon cycling, estimate the hydrological connectivity of wetlands to the watersheds in which they are embedded, determine the influence of hydrological connectivity and the atmospheric versus aquatic fate of carbon for wetlands in agricultural landscapes, and also develop web-based interactive computer tools for scenario analysis. And this is what's been happening in the reality over the past 3 years. And from what you can see, actually we did not deviate from the original objectives. In fact, we augmented some of the objectives, in particular, this objective now, it's not just about mechanistic process-based models, but we involve any type of data-driven and process-based modeling approach. But also it has been extended for carbon, nitrogen, and phosphorus cycling, and the deliverables from this objective are intricately connected with objectives 4 and 5. In addition, in terms of the hydrological connectivity, there is a lot of emphasis, as I will show shortly, connecting wetlands to other wetlands, the hydrological connectivity, but also wetlands to the broader watershed functioning. Objectives 3 remains the same, but we now include also both nitrogen and phosphorus. And in addition, with the web-based interactive approach, we strive to develop open source computer tools. And I will have a few examples, I will share a few examples shortly, that could be used indeed for all sorts, multitude of climate scenarios and assessing the impacts on the ecohydrology. Before we begin specific results, I think I would like to kind of share our vision, how we see this particular objective, and in the context of modeling and the different modeling tools that will be produced with this particular project. Sorry, the intent is we have all sorts of different models, both data-based and process mechanistic. We want to kind of create a library that will connect the different types of models, and loosely speaking, we have these 3 major categories that are connected, but they're not mutually exclusive. So what you will see today and moving forward is large-scale, basin-scale models that are intended to offer a regional assessment of high risk for carbon, nitrogen, phosphorus fate in transport. These are the models that are intended to offer the big picture, and usually they have coarser resolution and operate on a yearly scale. Again, just to offer the big picture that we try to obtain. But the next level involves more focused approaches at the watershed level, and their intent is to offer mechanistic understanding. These models are intended to answer questions of the type where, when, how, that is, identify hot spots, hot moments, and also allow us to gain mechanistic understanding, characterize certain paths that operate in the context of catchment and with emphasis on the role of the wetlands. And the next level, the more granular approach, the farm level approach, is where the HOLOS model in particular is. This is the level, the scale, where we believe the scale that matters the most, where actually we can make the difference with different practices. The idea is that the regional and the watershed level type of modeling will inform the HOLOS model and hopefully dictate future iterations and future augmentations. But at the same time, as was discussed earlier, there is a feedback loop in the sense that the HOLOS model, while we recognize the heterogeneity both in time and space, can be used to kind of extrapolate and obtain larger scale estimates. And since I'm showing catchment so far, we do not forget that the central, the focal point of all these models are the wetlands. So with that vision in mind, that's what I thought it would be better for the purpose of this presentation to show a few examples of that interplay between the different models, how models talk to each other, how information from one objective or from one modeling deliverable can inform subsequent models and so on. One important point that it is worth mentioning that significant monitoring, measurement, and modeling efforts revolve around two broader areas, the Lake Winnipeg and the Great Lakes Basin, which collectively host about 90% of Canada's agriculture. And today you will see a few results from Lake Erie, where we have, we are giving, we prioritized because there are all sorts of serious water quality problems, including the occurrence of harmful algal blooms and so on. Now, as just to kind of summarize, first of all, as an overview of the work that you've seen in the context of watersheds, what we're using is a multitude of GIS and airborne satellite imagery to detect trends in time, in space and time. And one of the driving questions has to do with the role of non-riparian versus riparian wetlands, different depths, deep, mid-depth, and shallow wetlands, and to what extent through surface and subsurface connections they are connected, and how they, with the stream drainage network, and how they impact the water quality downstream. Oh, we have a bit of a hiccup. Let me. Yes. Some of the noteworthy results over the past year come from Alice's group, where in their effort to map and characterize hydrological linkages between wetlands and the stream drainage network, they developed a machine learning methodology, machine learning simulations using the XGBoost model, powered by over 20 million observations, real observations and progress with fine resolution, about 500 meters. And using physical constraints in these models, based on drawing upon climate data, topography, geology, soil data, land cover, they are able to predict the groundwater table depth with a very promising fidelity relative to more conventional approaches, for example, physically based simulations based on Darcy-based numerical schemes. The results are actually very promising, and the publication, the paper has been accepted. It will appear soon in the journal Advances in Water Resources. In addition, ongoing efforts focus on classification of wetlands that act as sources or sinks of groundwater. Also, the characterization of surface versus subsurface connections. And also another challenging task is to identify the nature of these connections over time. For example, whether we have event-based ephemeral connections, seasonal or perennial. Another interesting highlight from Alice's work, in fact, I have here three of his students who are involved in his dream team that have been actively involved within the context of the project, is a way that they managed to address some fundamental weaknesses of the Bidaico curve in the prairie pothole regions. The problem was that, at least what we expect according to the theory, the runoff ratio in areas that have sufficient wetness, so aridity index lower than 1, that the value should be consistently above 0.2. That's not the case, as you can see on the panels on the right, the first column, and which is a clear weakness that Alice's team was able to overcome by introducing as a proxy the inundated area expressed as a percentage, and they seem to be getting actually a much better fit. The project is almost complete, and I believe they are working on a manuscript. Then we're switching gears, and just I'm going to offer you a few highlights from Irina's work and her dream team. Here, a few members of the team that have been working quite actively in elucidating certain features of the wetlandscapes, this network of hydrologically connected wetlands, assess their variability in time and space, and also can identify how they are being affected, their features, by climate change and other anthropogenic disturbances, and subsequently affect the water quality. They have been using a number of important predictors, temporal predictors, climate, precipitation, temperature, but also a number of proxies to characterize inundation connectivity and also inundation morphometry. And ultimately, the assessment, as you will see shortly, was to see to what extent how wetland gains or losses affect carbon, nitrogen, and phosphorus loading into the Great Lakes. One important finding that it is worth to discuss today is the fact that wetlands can be clustered into headwater upper reaches associated with stream orders, stream orders 1 and 2, middle reaches 3 to 6, and lower reaches 7 and 8. And what you see here on the right panel is the time series of the wetland area connected to each stream order group relative to the total stream connected wetland area. And you can see that for the first and second order streams, it is approximately 70%. For 3 to 6, approximately just shorter than less than 30%. And for 7 and 8 is less than 1%. Another exciting finding is that the role of the headwater gatekeeper wetlands, and they have been overlooked in the literature. And based on some random forest modeling that Irina's system conducted, they found that a critical feature, the headwater wetlands, can play a significant role depending on the degree they are connected or not with the stream drainage network. Nutrient loading tends to be lower when the headwater wetlands remain disconnected, and highest during episodic reconnections. And from what you see on the right panel, as part of their modeling exercise, the best predictors is, again, the extent that they are connected with the stream network for first and second order wetlands connected with first and second order streams. This pattern tends to be weaker and perhaps have the opposite effect as we focus on stream orders 3 to 6 or higher, 7 or 8. How now? How do we connect this modeling work using random forest, machine learning into something more conventional? And this is where the Sparrow model comes into play. The Sparrow, the specially referenced regression on watershed attributes model, is USGS and endorsed model. I'm showing here some members of my team. And is founded on the concept of the nested watersheds. It is relatively coarse, the high resolution at the level of reach, but it has been used extensively for continental, regional, but also watershed-based simulations. Sorry, I rephrase, not simulations, statistical modeling exercises. It is effectively a nonlinear regression model, and we like it as an approach. Why? Because it is statistically driven, so it tells us the story that our datasets have, but at the same time, it has a bit of a mechanistic flavor in the sense that the loading, what is being exported from a watershed, can be dissected into a few major processes. One is the nutrient export or the carbon export from different land uses. The second is the land to water delivery. And it also considers stream and reservoir / wetlands attenuation. It has been used in the literature predominantly for total phosphorus and total nitrogen, but we expand. Here's now one graduate student that is co-supervised with Irina to extend it with dissolving organic carbon and dissolve organic carbon. And the main requirement is that to have a sufficient spatial coverage of the model domain. So it requires many sites in space. It is not temporally explicit, or at least for the majority of the applications. And one interesting piece that we're trying, a novel piece that we're trying to introduce, is that when the data are not fully available, so the coverage is not up to our expectations, we have the option to use Bayesian inference techniques, where along with the data that may not be ideal, we have some information, but they are not ideal, we can further support and augment the modeling exercise by introducing information from the literature, draw information from the literature for the different coefficients that are being used. Now, these are different proxies that have been used in the literature for the different processes, for the land uses, for example, for the land to water delivery factors and the stream network. What is the piece that I wanted to draw your attention is that there is considerable confusion about how wetlands should be treated. And we have seen in the literature approaches that introduce the wetlands as a different land use and quantify their export. Other approaches have used the wetlands as a proxy to estimate the land to water delivery. And other approaches, which is the one that we gravitate towards now, is to use them as a potential as a potential recipient of carbon, nitrogen, and phosphorus, and depending on their location, we can determine to what extent they act as sinks or as sources. This is the novel aspect that we're introducing with this project, and it is directly connected with the work that Ali and Irina have completed recently. A few highlights from our application to Lake Erie. In Lake Erie, we have the luxury to have many data points. The issue was that we do not have a sufficient number of sites where flow stations and water quality monitoring stations are collocated. So we had to be a little creative in that regard to achieve, to obtain a sufficient sample size. We introduce also the potential error associated with that quote-unquote creativity. And with that in mind, what we have here is one snapshot that you can get from Sparrow, which is the export of phosphorus in this particular case for cumulative on the left and at the level of rich and normalized per area on the right. The pie chart on the bottom shows the contribution of different land uses. And from an export point of view, one highlight of that work is that the local greenhouses are responsible a great deal for the exported phosphorus from that watershed. But there is also sufficient distinct footprint from cropland, and also on an aerial basis, we see that the urban sites, they have significant contribution. This is the same sort of information, actually an attempt to provide a first attempt on the phosphorus cycle among the different land uses that are being considered on the left for the different counties within the broader Lake Erie basin. And also we quantify what is being exported in Lake Erie, a significant fraction, and what is being lost in the streams and the wetlands in the area. One thing that is important to clarify here, at this point, the wetlands are being treated as if they are connected to the stream network. So the idea, the findings that were presented before are not explicitly accounted for yet. Meaning that at this point, as we speak, the model predicts that the wetlands are responsible, are acting as a sink, but they attenuate the exported phosphorus by less than 3% as a total. With the new approach, with the new findings, we will be able to reassess to what extent this result is robust or to what extent they play a greater role in the area. In the same spirit, but I won't go into great lengths, we have a similar approach for Lake Winnipeg. And we're able to kind of delineate the footprint of agriculture in the Lake Winnipeg watershed. Now, so far we're talking about phosphorus, and it is predominantly an attempt to connect agricultural activities with the phosphorus export, and also to what extent wetlands fit in that context and what is the role. Now we'll switch gears and we're going to focus on greenhouse gas emissions and an application, a large-scale application in the Lake Erie watershed. Since there is a talk from Ronald tomorrow about Hollows model, I will spare the details. We'll have the opportunity, I believe, to discuss extensively about current features and about, exciting prospects that we see here. For now, what I will share with you is a few key highlights from the work that was completed in the same location where we attempted to characterize the phosphorus export in the Lake Erie Basin. So what you see here is on the right the two maps that quantify greenhouse gas emissions per county. And on the top is total greenhouses. On the bottom, they are normalized per area. It is interesting that there is a mismatch between the hotspots of phosphorus that occur in the areas where we have the greenhouse gases on the western end of the Lake Erie Basin, whereas the highest greenhouse gas emissions are associated with the northern eastern part of the Lake Erie Basin. On the left, you'll see an attempt to kind of distinguish between the contribution of the livestock against the crop activities that are in the area. And we have applied the Hollows model for 4 years, 2001, 2006, 11, and 16. The next slide shows in a similar Sankey diagram the contribution of the different counties on the the greenhouse gas emissions through different paths. enteric methane, manure, direct nitrogen oxide, indirect nitrogen oxide, and also farm energy, just to kind of see what the different counties contribute and how. It will be great oversight if I do not show Ratnajit here, who happens to be also in the same office here today, as part of, this is part of his PhD, the second and the third chapters of his PhD. And after a discussion with Ronald, we're actually now in the phase of assessing the sensitivity of some of these projections on assumptions that we made. And what you see here is the emissions per county when we change one single factor, and that single factor was the diets of the livestock. We tried 7 different diets. One is the diets that are being reported in Omafra for Ontario, and 6 others are based on what we're able to find in the literature, based on common practices in the area. What is noteworthy here is not the actual predictions, but the error bars that you see around these fluxes and the considerable uncertainty that they reflect. That's something that potentially tomorrow we can discuss about how this can be controlled, can be constrained, or to what extent it can be verified. And after in the same area, we have now what first approximation of the phosphorus cycle and greenhouse gas emissions from the agriculture. The next step is to see what is the role of the wetlands in that broader area. We have approximately as an area the distribution of the different wetlands as bogs, fens, marshes, open water, swamps, and so on. And I felt that this is a good point to introduce the mechanistic modeling work that is being done. In the proposal, we did indicate that it will be helpful to introduce a mechanistic model that will allow us to offer a platform to generate hypotheses, to examine different scenarios about the importance of different paths and so on. And we opted for a multi-elemental approach. Here you see Yuko and Natalia, 2 members that are actively working the development of this process-based model. And this is just a snapshot of how the organic cycle will look like. The different state variables that are being considered and the associated processes. We give a lot of emphasis also on capturing, at least representing the interplay between the macrophyte community, so we consider submerged, immersed, and vegetation and free-floating plants, and the potential, depending on the nature of the wetland, to support primary productivity in the form of phytoplankton. The model is complex, clearly, but I will elaborate a little bit on how much information we have to support that complex model. But the idea was to kind of have an inclusive platform, open source. Not every single model has to be active in any application, but it could be a model that through this process of adaptive inclusion of information as it is being produced, it can be improved, we can reformulate certain processes and so on. So it will be an open source tool. We give also a lot of emphasis in capturing these processes, to what extent they drive the oxygen in the water column, and subsequently they affect the nature of the aerobic and anaerobic zone, as well as the intensity of the sediment diagenesis processes. Before I proceed with needing a little bit more information about this process-based model, there is also a recent addition. We're very excited about it. Betty Ekvall has joined the project from Sweden. And the objective of here to support the mechanistic modeling work her expertise is in peatland wetlands, and the idea is that she will apply mechanistic modeling in two sites, two triads of natural, drained, restored peatlands in two different sites in Sweden, one in the north and one in the south. The idea is they have a wealth of data that can support a more mechanistic, more complex exercise. And the idea is to learn from her work to see to what extent some of this information is transferable in a Canadian setting. And also assess potentially the processes that need to be revisited moving forward, especially since the sites that Betty will have the opportunity to model are relatively well studied.
George, can you wrap it up in 2 minutes?
I think about 4. But I'm working on it. Okay. So really quickly, just to tell you that this is an approach, but where in the again, the vision is to create a library of models, not just a single model. So we're reviewing the literature, and hopefully we'll be in a position next year to kind of have a more systematic presentation overview of the models that are available and can be used to address different types of questions. Since I exceeded my time, I'm just going to tell you that Yuko, who has significant experience from past work to evaluate meta-analysis, to evaluate certain models. For example, 9 years ago, she completed a review of the models that evaluated the capacity of the current generation of biogeochemical models to recreate the dynamics of cyanobacteria. And now she reviewed what do we know about the parameters or the mechanisms that have been introduced into our mechanistic model. And what you can see here is that in terms of the plant, the macrophyte and phytoplankton, but mainly macrophyte growth, there is a wealth of information. There seems to be less info so far based on her review about other biogeochemical processes pertaining to the carbon cycle. And this slide here kind of distinguishes between the different types of wetlands or processes that are associated with effects of temperature, with light, with nutrients, and so on. So this will be one of the deliverables that we will provide. We will create a database for different parameters based on empirical rates and so on, something that will facilitate the implementation, the usage of that model. And really quickly, an additional angle that connects with the objective 5. We also study the connections between wetlands and biodiversity. There is, at this point, there are 78 species at risk that are connected with wetlands. And Jean here is responsible for this aspect of our research. Based on in the context of climate refugia, there are different scenarios of the conditions that will emerge. We have the ex situ refugia that refer to species rates that will be beyond the current ones. In situ refugia, no changes. We have micro refugia, small microenvironments that could potentially protect species at risk, and macro refugia. The idea that we're working on right now is to identify scenarios where we can experience co-benefits could emerge. And the nil hypothesis of this approach is conveniently expressed as, that indeed there are co-benefits where we can achieve greenhouse gas emissions and biodiversity or water quality could improve. But based on evidence that we compile, we see that that's not always the case. They're either independent or in some instances what we have is an optimal sweet spot where we have the maximal benefits. Beyond that sweet spot, we have the point, it's that point of diminishing returns. Since I do not have time, I will be really quickly. If there is a single point that I will highlight for this particular objective as next step, we need to reach out as a group, collectively and individually, to colleagues, PIs who are involved with objectives 1, 2, 4, and 5, especially 1 and 2, and capitalize upon the great data that are being produced. Because at this point, we need to determine what will be the optimal models to start producing estimates, identifying hotspots, hot moments, and so on. Thank you for your attention, and my apologies if I exceeded the allocated time.
Thank you, George, for a really interesting and comprehensive presentation. We have 5 minutes for left in the Q&A, and if there's a lot of questions, I don't mind giving up 5 minutes of my time for Objective 4, but I hope that we can get a discussion started on this topic. Let's start with Christian.
Hi, George. Thank you very much for the presentation. I was really intrigued by your modeling of the phosphorus exports, as you might imagine. So I think it would be really great if I connect you to my master student, Shir Gruber, to see whether her data set can somehow be integrated into your models. And the more specific question I had was about, okay, screenshot of the slide, but it has no number. It had the header spatially referenced regressions on the watershed attributes, where you showed the export in Southern Ontario.
Do you have specific question on output or the model itself? I'll be happy to say.
On the output, not the model. So you have the left side of the figure shows the total phosphorus in tons per year.
Yes.
Does that refer to the total amount of the counties, or are those counties that you have shown there?
Actually, yeah, thank you. That's a very good question. For phosphorus, we are not using counties. We are using as the scale of reference are the delineated sub-watersheds within the broader Lake Erie Basin. And what you see there is the total amount of phosphorus that is being exported from the land uses. We do not account any attenuation in stream or in the reservoirs, wetlands, and so on. The total amount per sub-watershed. The one next to it refers to, we are normalizing it per area of that catchment. And the difference is that whilst as a total amount, clearly the agricultural land, cropland, is the predominant driver. However, once you normalize per area, you can see that overwhelmingly, it's a major issue now, that the greenhouses in the area of Leamington are the primary driver. And even more important is that what you saw in that slide, it was expressed as total phosphorus. That particular location also experiences by far the highest levels of dissolved phase phosphorus, which is readily bioavailable and can trigger some of the hubs that we see quite regularly in Lake Erie. In fact, we did, clearly that's not really on the scope of the project yet, at least. We did some modeling for the receiving water body, and what we saw is that depending on the hydrodynamic patterns, what's coming from the Momi watershed, river watershed, which is multiple times higher, is totally unrelated. So major blooms can be triggered only from the greenhouses.
Thanks, George. We're going to move to the next question to Ben.
Thanks, Irina, and thanks a lot for that interesting talk, George. I think my comment is similar to Christian's in that I want to just alert you to that the fact that we may also have data sets that might be interesting to you. And so to that effect, I was just wondering so you mentioned that you were looking at bringing in wetland type data in your Lake Erie greenhouse gas models. I'm wondering if you would also possibly be interested in surface water dynamics. So looking at how surface water extent in those wetlands might change over time. And would that be useful for your modeling?
For what is worth, Ben, I just saw, I do not know exactly, but that's part of the fact that we need to reach out. We're not connected. I saw, I think it was Dev's presentation, and what you folks are producing is directly related with what we're about to embark as a next step to augment the Sparrow model.
Nice. Yeah, because I think what might also be interesting to you is that through this subpixel water fraction approach that David was explaining earlier today, we can map water dynamics not only in the wetlands themselves, but especially in the Lake Erie Basin. We actually observe quite some surface water dynamics in the croplands themselves as well. So we're able to kind of disaggregate those to a certain extent. So just alerting you to that fact, if that's interesting for your modeling approach, we should definitely stay in touch.
Highly relevant. It is an oversight that has not happened yet, but definitely it is very interesting, very relevant to our work.
Good. Thank you.
Thank you.
So I feel a little bit like this is like a date matching thing, like people can hook up after, but I have a question of my own, George, and I'm reflecting on the beautiful data set that Pascal showed from Tim Moore, Christian, and Rico, and I was wondering, because we're so constrained about being able to take similar wetlands that go from intact to drained to restored and looking at the changes in biogeochemistry, do you think that we could develop a model that uses the time series locked in the soil profile and use that to help predict the changes in the carbon fluxes as you go among the triad from the intact, drained, restored, and freshwater mineral wetlands? We have that type of data not only for Alberta, which is the data that was shown, I think it was Camrose, but we also have it for sites in Ontario, similar kind of chronosequence. And I'm just wondering, do you think that we can develop a simple model using that information to predict the effects of land management on the carbon fluxes?
In principle, yes, absolutely. And there are several ideas that we can try. Ultimately, we'll see to what extent the data will help us to find statistically robust relationships. But again, even if that condition is not met, the whole idea that we operate, as you may recall, even from the beginning or when we were writing the proposal, is that even the relationships based on the current data, they are not particularly strong. We can communicate the uncertainty and sequentially update these relationships as more information becomes available. That's the whole thing of the Bayesian element that we introduced at the time.